Good afternoon to everybody. We are going to start the solution of problem 5. That the statement of problem 5 is the following. An aluminum post is fixed at the base and is subjected to a load T, a force T, as shown in the picture. We have an angle alpha that is equal to 28 degrees, and the height of the post is 2 meters with a tubular cross-section. The question is to determine the allowable tensile force in the cable if the maximum allowable compressive stress in the material is 80 megapascal. So first of all, we have to project the force in the upper cross section of the post. This is the upper cross section of the post, okay, and we can split this force in two forces: one horizontal force T sine alpha, and one vertical force applying in this corner of the cross section that is going to be T cosine alpha. Okay, then the next step is to move this vertical force to the center of the cross section. Okay, this is more or less the center of the cross section, so we can keep this horizontal force in the same line of action, T sine alpha, and this vertical force here at the centroid, that is T cosine alpha. And we have a moment that is something like this because of the translation of T cosine alpha from this corner to the centroid. Okay, this is T cosine alpha multiply the outer diameter d2 divided by 2. Okay, then as the lower cross section is the critical cross section in terms of maximum bending moment because of the shear force, we have to take into account that there is a different bending moment at the lower cross section. Okay, so let's draw the lower cross section. Okay, this is the cross section in the fixed support, and now what we have here is an axial load that produces compression. This axial load has the same value as before, here more or less T cosine alpha. Then we have the shear force here, that is T sine alpha, and we have a bending moment that is the addition of the previous bending moment T cosine alpha d2 divided by 2 plus the effect of the shear stress multiplied the total length, that is T sine alpha multiplied by L. Okay, according the statement, we have L equal to 2 meters. Okay, in this condition we can write the normal stress distribution in the lower cross section sigma n x equal to minus T cosine alpha divided by the area of the cross section, the tubular cross section, plus we are gonna check this thing later on, plus the complete bending moment T cosine alpha d2 divided by 2 plus T sine alpha multiplied by L divided by the moment of inertia about the z-axis, for example, if we consider that this is the cross section. Okay, this is the inner diameter, this is the outer diameter, and this can be the axis, for example, y, axis y, and this can be, for example, the axis z. Okay, z axis. So if we consider this projection of the cross section, we will have the bending moment about z. Okay, so this is the moment of inertia about z, and we have to introduce here the y coordinate. Okay, and now we check this value. Okay, if we have this bending moment, we need to have compression in this part of the cross section. This means that when y is positive, we need to have compressive force. Okay, so the correct thing is minus here, minus. Okay, so in this lower cross section, we have the condition is that this maximum normal stress, the maximum normal stress in compression, okay, that is produced when y is positive, okay, when y is positive, this maximum compressive stress is lower, okay, than 80 megapascal. 80 megapascal, and this when y is equal to d2 divided by 2. That is, in these points we have the maximum compressive force. Okay, so let's calculate that value. Here we have to consider that this is an absolute value. Okay, so we introduce this condition. Okay, absolute value. Okay, absolute value. Okay, so if we calculate the actual value, we have to take into account that the area of the cross section is equal to number p d2 square, d2 divided by 2 square. Okay, minus number p d1 inner diameter divided by 2 square, and the moment of inertia about the z-axis is equal to number p d2 divided by 2 to the 4th power divided by 1/4 minus number p d1 divided by 2 raised to the 4th power divided by 4. Okay, taking this into account, we can state, or we can calculate the normal stress when y is equal to d2 divided by 2, and we have the absolute value, all of this positive, that is t cosine 28 degrees divided by the area of the cross section plus t cosine 28 degrees. If we work in meters, we have 0.250 divided by 2 plus t sine 28 degrees multiplied by 2 meters. All of this divided by the moment of inertia about z, and multiplied by this absolute value 0 to 50 divided by 2. Okay, and this should be lower than 80 megapascal. Okay, if you work in pascals, you are gonna get these numbers: 49.96 T plus 1036.75 T plus 121.87 T must be lower than 80,000 Pascal, and that means that T has to be lower than that maximum, that is equal to 66.13 kilonewton.